Welcome. We are in Module 3, Reactor Design and Cost Estimation. In the two previous lectures, we saw the basic reactor types or the design equations for the reactor. Then in the previous lecture, we saw various types of chemical reaction and then whether we can generalize these reactions into certain categories like elementary, non-elementary reaction, biological reaction, so on and so forth. Then we saw the catalytic reactions, what are the typical characteristics of the catalyst that are used in the in industry. Okay. And in this lecture we continue the theme and then we shall see now the types of reactor in greater detail, basically the design of the reactor. The previous reactor type was of general type like a back mix reactor or a plug flow reactor or continuous stirred tank reactor, but in this lecture we shall see specific reactor types and design depending on the application. We categorize these reactors in two sections: the fluid reactors, the reactors that treat either two liquids or gas liquid or gas, and the second type of reactor is a heterogeneous, that is fluid solid reactors. Then we shall see the criteria for selection of reactors for a particular application. We take the theme further to see the design and costing of reactor, and finally we shall solve a problem for the design and reactor cost estimation. So let us see the first topic, that is the type of reactor. I already told you that basic reactor types are two: the back mix reactor and plug flow reactor. The back mix reactor are either batch reactor, in which the reactants are taken once and the system is closed till the reaction is carried out, okay, or it could be a continuous stirred tank reactor, whether the contents are mixed like a CST, like the batch reactor. However, the reactants are continuously added and products are continuously withdrawn. The second reactor type is the plug flow reactor, where the reactants flow continuously in one direction in a tubular cylindrical vessel. That is what the plug flow reactor is. Depending on the type of reaction, we have to provide the cooling or heating. We can provide cooling or heating either in the form of jacket or in the form of cooling coils that are either inside or outside the reactor, surrounding the reactor. And the reactor should be so designed that it withstands the operating condition, especially in case of reactions that use harsh operating conditions such as high temperature, high pressure. Okay. The material of construction is another issue that we are going to address later, but the reactor should be so designed that it withstands the operating pressure and temperature. NPTEL also has special courses on process equipment design. So this topic will be covered in greater detail in those courses. So I do not include it here. Okay. So here we shall see only the process design of the reactor. Let us see what are the means of providing heat or removing heat from a particular reactor. Here you can see three types. First is the internal cooling coils that you see here. The coils are especially on the periphery. Okay. If you see this as a 3D reactor, the reactor coils, the cooling coils are especially on the periphery and the agitator is provided in the center. Okay. Then the cooling coils can be also attached externally, and here they wrap again on the surface of the reactor, or it could be a cooling jacket. Okay. The water inlet is at the bottom and then flows at the outlet. Okay. Now, depending on the exothermicity of the reaction, you can provide either a jacket or a coil or both. Okay. In some cases, extended surface is also provided, like certain surfaces which have the cooling coils attached on the periphery. So those are for highly exothermic reactions like polymerization or Fischer-Tropsch synthesis. In addition to these, we have to provide certain facilities for addition and removal of reactant. Like for example, we have to provide vents in case of pressure surge then pressure release valves, then sampling inlets, seals, and auxiliaries for agitation. So depending on the reactor type, these additional facilities will come into picture. Apart from that, the reactor should have adequate foundation, either concrete or steel or both supports. Then we have to provide facility for personal access. Like providing manholes in the reactor or inspection. We have to provide the view windows over which we can, like glass windows to the reactor through which the operator can see inside the reactor, and certain provisions for the maintenance. Now maintenance means small scale maintenance. It is not like shutting down the reactor and cleaning it thoroughly. Small scale maintenance like providing certain holes where we can put in the cleaning equipment and unclog the holes or something like that. So those maintenance provision should be made. Okay. Then special attention is to be given for agitation in case of stirred tank reactor design. Now most of the reactors are stirred tank type reactors because the reactant mixture has to be agitated, and correct agitation is critical for reactor performance. Okay. Now criteria for correct agitation. Criteria for selection of agitator. We have to first see the physical properties of the reactants. What is the density? What is the viscosity? If the reactants are highly viscous, we cannot provide agitation at high rates. Okay. Secondly, if we want to have, like for example, like juice concentration, if we want to have operation for a thermally degradable reactant, then we have to have agitator of special type. It should not cause mechanical damage. Like for example, in case of biological reactions like fermentation reactions, etc., if the mechanical agitator is rotated at high RPM, then it can cause damage to the cells. So usually the agitation in those cases is provided by gas flow, okay, so that it does not create any shear stress on the reactants. Okay. So depending on the physical properties, depending on the sensitivity of the reactants to agitation, their mechanical stability, okay, delicacy, or if the reactants are very fragile type, then also the agitator has to be designed properly. For example, many catalytic reactions, the catalyst particle tries to break down, because if the support is not sufficiently strong, the catalyst may get fragmented due to collision on the reactor wall in case of intense agitation, and therefore we have to select the agitator accordingly. Like criteria for selection is physical properties of reactants plus the flow pattern that is needed in the reactor. I will show you certain standard agitators that are used in industry. The first one is the propeller, okay, which creates basically an axial flow of the reactants. Then the turbine, which is flat blade turbine, which creates basically a radial flow of the reactants. Then the third one is a pitch blade turbine, where the blade is given certain angle. Now this is very much like the ceiling fans that we use in our home. Now here the flow that is created is both axial as well as radial, so it is essentially in this direction. Okay. So and then there is paddle wheel, which is used in some cases. Then anchor type if the reactants are highly viscous, and then in some cases the helical ribbon type of agitators. So these are some of the common agitators. Now here anchor type creates a radial flow, paddle also creates a radial flow, helical ribbon type may create some flow in axial direction as well, okay, similar to pitch blade turbine, so on and so forth. So depending on the flow pattern that you want in the reactor, you have to choose this agitator. Okay. Now this is as far as the fluid reactors are concerned. In some cases, some flow reactors have large cylinders through which the reactant flows, while others are designed in the form of multiple tubes located in parallel with the reactant flowing inside the tubes. In these cases, where the reactants is distributed in multiple tubes, okay, you can assume the reactor operation to be ideal plug flow, because the extent of back mixing is very small. As the diameter of the flow increases, the extent of back mixing also increases. Okay. So that point we note here. In case of flow reactors, the extent of back mixing depends on the diameter of the vessel. For reactors in which the reactant flow is distributed in multiple tubes arranged in parallel, the flow can be assumed to be ideal plug flow, as back mixing is small. Okay. Now this is as far as the fluid reactors are concerned. Now the topic of fluid solid reactors. These are essentially the catalytic reactors. Now use of catalysts requires special reactor design to account for the mass and energy transport issues. Okay. Here the mass transfer limitations are more pronounced. Okay. There are various designs available based on the relative motion of the reactant. The three basic type of reactors are either a single fixed bed reactor. I will show you a basic sketch of these reactor types. The first basic reactor type is a fixed bed reactor, in which the bed of the catalyst is enclosed in a shell and the reactant flows over it. Okay. Below and above the bed there is a distributor. Now if the reaction is exothermic, then the cooling may be provided simultaneously. Okay. So this is a basic fixed bed type of reactor. In case where the amount of heat that is released is quite high, then fixed bed reactor may not be very useful, because the convection in this type of reactors is very small. Therefore, the transport properties are not very high. For example, you are not going to get very high heat transfer coefficient in these kind of reactors. Okay. Therefore, we have to go for a fluidized bed reactor. Now, fluidized bed reactor contains fluids that are suspended in flow of the reactant. Fluidized bed reactor is essentially a vessel which has a tapering end at the bottom. The reactants enter and in the form of basically gas or liquid or mixture, and these are distributed into the reactor through a distributor plate. A distributor plate could be of different type. It could be a simple perforated plate, or it can have certain like tuyeres or caps, bubble caps. Okay, those things are, those details are included as per the need. Okay, but basic thing is that you have a distributor through which the reactant fluid is spread into the reactor, and then small particles of catalyst are suspended in it. Okay. Now, if we have to suspend these catalyst particles into the flow, obviously the velocity of the reactants has to be higher than the minimum fluidization velocity. Okay, that is determined by another force balance on the particles. So, those things we are not going to include in this course. You have a separate course on fluidization engineering where these things will be covered in greater detail. Now, depending on the velocity of the reactant, these particles move around. So, you get different regimes of fluidization like bubbling regime, churn regime, or fast fluidization, turbulent fluidization, and in case where the flow of reactant or the velocity of the reactants exceeds the terminal settling velocity of the particles, then these catalyst particles may get carried away, and then you have to, at the outlet, you have to capture these particles in a cyclone separator and return back to the bed. So, this is like the fluidized bed reactor. Fluidized bed has two operating regime, bubbling bed or bubbling or turbulent, and second is circulating fluid. These reactors have everything mixed, so the performance of this reactor is very similar to CSTR. Then the third type of reactor is a moving bed reactor. These are especially used when the fouling is high or catalyst deactivation rate is high, so that you can continuously remove catalyst from the reactor and then regenerate it. Here the reactants and the catalyst particle flow counter current to each other. Reactant enters at the bottom and the catalyst particles are added at the top. However, unlike the fluidized bed reactors, here the velocity of the reactants is sufficiently small, so that all the flow occurs between the voids and there is no movement of the particles in the direction of the reactant flow. So, particles move continuously down slowly, and these are removed, a side outlet. Then these catalyst particles are treated and then sent back to the reactor. So, these are the general solid fluid reactor types: fixed bed, fluidized bed and moving bed. Now, depending on particular application, there are several sub designs, sub categories or further detailed designs that I will show you now. One design is that of a basket reactor, in which the catalyst is put in a porous basket. That basket rotates in the reactor at high velocity. So, the reactant can access the catalyst particle through the pores of the basket and the products flow out. Reactant flow can be unidirectional, the flow enters at the top and leaves at the bottom. Then second is slurry type of reactor. Here the reactions with slurry containing solid particles that can be physically separated by suspension fluid are carried out. The tank is agitated tank. These reactors are simple in design and they have good transport properties, especially for highly exothermic reaction, and then control can be provided, as sufficient control can be provided over the reactor conversion, reactor performance without any compromise to catalyst access. In fact, catalyst particles can be added or removed also continuously through the flow of slurry. However, the one major demerit is the erosion in this reactor. The reactor erosion occurs because of the speed of agitation is high, and therefore impingement of the reactor particle over the reactor wall can cause certain erosion of the reactor wall, as well as it can cause fragmentation of the particle. Okay. Then the next is the multitubular reactor. Multitubular reactor, as I already mentioned earlier, the catalyst is the reactant is distributed. Reactant flow is not through a single bed, but it is distributed through different tubes. There is a distributor down here which spreads the reactant almost uniformly over all the tubes, and the catalyst is packed in these tubes. So these are like multiple fixed bed units where multiple beds or catalyst filled tubes arranged in parallel, and heat conducting fluid can flow outside these tubes. You can achieve good thermal control and uniformity of residence time distribution in these type of reactors. Then comes the circulating flow reactor. Circulating bed, which I just mentioned, is like the moving bed reactor. These are essentially same as fluidized bed reactor, but they create suspension of particles through fluid impingement. Okay. Like in some cases, spouted bed reactors are used, where the reactant flows through a shallow bed of catalyst particles, and then it lifts the catalyst particles slightly so as to create more voids or more mixing. Okay. So these are the moving bed, or sometimes called as spouted bed reactors. These are these are like the family members of fluidized bed reactor itself. Okay. However, the velocity of the fluid motion is relatively small. Then there are like thin or shallow bed reactors in which the reactant fluid flows through catalyst mesh or thin beds, and these are suitable for fast reactions where good control is required over the residence time distribution and temperature. These are quite simple in construction and particularly useful for catalyst reactivation, maintenance and removal of larger heat load. Then comes the category of dispersion reactor. Now there are two types of dispersion reactors shown here: gas dispersion and liquid dispersion. These are typically fluid containing vessels that allow dispersion of liquid and gas phase reactant by bubbling the latter through the liquid or dripping the liquid in the gas stream or into less dense liquid. Like in the first reactor type, the gas is bubbled through a reactor. In some cases, the gas sparger is used, a ring which distributes the gas uniformly throughout the reactor vessel. In case of large diameter, okay, the liquid flows continuously. In case of liquid-liquid reactions, the lighter liquid is sparged from the bottom. Again, there is a distributor here which spreads this particular liquid in the form of droplets, which move upward through a denser liquid, and then the light liquid is taken out at the bottom. The heavy liquid can also be in the flow mode. It can enter continuously at the top and removed at the bottom. Okay. In some cases, film reactors are used. This design is to maximize the contact area for gas liquid reactions by bringing together a gas and liquid as a thin film over solid support. These reactors also offer increased thermal control due to solid support, like a packed bed reactor, over which a counter current operating packed bed reactor using certain packing like Paul rings, Rashi rings, IMTP packings. In this case, the liquid is spread in the form of a thin film that flows over, or it wets the packing surface, and the gas flows at the bottom, and because of this spread of liquid over the packing surface, very high interfacial area can be achieved. In some cases, they also used wetted wall column reactor, where the liquid is spread over a particular column which wets the wall of that particular column. This is especially for low surface tension liquids, which can be easily spread in the form of film. Okay. Now we shall see the criteria for reactor selection. Which reactor is useful for which application? Criteria that we need to consider are temperature and pressure of the reactor, then second, need for removal or addition of reactants and products. Then third, the required pattern of product delivery, whether batch or continuous. Then the catalyst type and use, requirement for solid catalyst replacement and contact with fluid reactants and products, then the relative reactor cost, then the operational or process limitations, and then safety, environmental factors. So on and so forth. Now NPTEL also has 2 courses on safety and risk assessment. So that point will be treated in greater detail, last point will be treated in greater detail in those courses. Okay. In some situation, multiple reactor types could be used depending on the consideration of the cost, safety and other issues, like there may not be a complete PFR or complete CSTR, like conversion of reactor may not be achieved in a single reactor. There could be reactors in series, okay, or there could be reactors in parallel. Suppose the reaction is highly exothermic, like these things we have seen in module 2 also. If the reaction is very highly exothermic, then the amount of heat transfer surface that can be accommodated in the single reactor is high. Therefore, it may not be possible to treat the entire reactant in a single reactor because of the size limitation. The maximum amount of heat exchanger area that you can stuff in a single reactor is typically 6,000 to 8,000 feet square. So accordingly, you have to distribute your reactant in different reactor types. Many times in case of highly exothermic reactions, in case of hazardous reaction, corrosive reactions, okay, standby reactors could be used, so that one reactor, if it malfunctions or if it is under maintenance, the second reactor can operate. Okay. Or some reactions can be carried out partly in a PFR, partly in CSTR. Those things also we have seen before module 2, where the contacting pattern depending on the order of the reaction, the kinetics of the reaction. There are no explicit guidelines for selection of reactors, but we can have some rules of thumb which we can use in selection of appropriate reactor for given application. I will now summarize some of these rules of thumb. For conversion up to 95% of equilibrium, performance of 5 or more CSTRs connected in series is equivalent to that of PFR. For conversion up to 95%, performance of 5 CSTRs in series is equivalent to that of 1 PFR. Okay. Then CSTRs to be used for slow liquid phase reactions or slurry reactors. Okay. Then third, batch reactors are best suited for production in very slow reactions, or those which foul the reactor, or those which require intensive monitoring and control. So 3 criteria for selection of batch reactor: very slow reactions, which means very high residence time of the reactants, that will give very high volume of PFR, which is impractical. Then if the production scale is small, and third, fouling, intensive maintenance and control. Okay. That is what the 3 criteria for batch reactors. Then in case of catalytic reactions, the size of the catalyst particle is crucial. The typical size of catalyst particles 3 millimeter or 0.003 meter for fixed bed reactor, because here you have to use a slightly larger size so as to have sufficient voidage, because if the voidage decreases, then pressure drop across the fixed bed decreases. Increases, pressure drop increases. So in order to have a judicious choice between interfacial area and pressure drop, 3 millimeter size is typical. If you go above this, then you have higher voidage but lesser surface area. Then for slurry reactors, 1 mm size. And for fluidized bed reactors, 0.1 mm. Now, fluidized bed characteristics, in fluidized bed, the hydrodynamics and kinetics are very finely interwoven. Okay? If you use a larger particle size, then the terminal settling velocity increases. So the UMF increases, the minimum fluidization velocity, okay, and then the residence time of the reactants decreases. So in that case, the particles are characterized as C, B, A and D. C for cohesive, B for big particle size, A is the actual size, which is typical catalyst size which used in case of FCC, and D is the very large size, that is in case of spouted bed reactors. Again, you have a course in NPTEL on fluidization engineering, also on particle characterizations. So these topics will be treated in greater detail in these courses. So we leave these things right here, okay, with introduction. Then the design of reactor system. Usually number of connected reactors are more economical than a single reactor. This also gives you certain flexibility for maintenance and product distribution. The reactor combination or arrangement for optimal production of a product is subject of analysis. The criteria is same as for single reactor with added issue of arrangement of these reactors. So if you want to split one CSTR into three CSTRs, then you have to adjust the intermediate compositions properly so as to have the same overall conversion as in case of a single CSTR. Generally, for nth order elementary reaction where n is greater than 0, reactors are connected in series. Reactant concentration should be kept as low as possible if the reaction order is less than 1, if n is less than 1, and as high as possible for reaction orders greater than 1. For complex reactions where the reaction rate has a minima or maxima, okay, with respect to reactant concentration, there is no simple guideline. Okay. Therefore, these things have to be treated from like on case to case basis. Different conversions for same reactor system may call for different reactor combination and arrangement. Graphical methods for reactor design are quite useful. Again, you have two courses on chemical reaction engineering in which these things will be treated in greater detail. The graphical methods, typically for a PFR, the area under the curve, reaction rate curve, okay, versus conversion gives you the volume, and in case of CSTR, it is that square or rectangle of conversion that gives you the reactor volume. Okay. So basically graphical methods are useful for initial design, and after you get a order of magnitude or some idea of the volumes that are required, okay, then you can go for the further design. Then comes the topic of costing of the reactor. Design and cost of reactor vessel are handled in a similar manner as for the pressure vessels. Now there are several cost correlations that are available. What we see on the screen now is the installed or purchase cost of kettles. Okay. Cost includes the kettle, jacket, agitator, thermometer well, drive and support, manhole cover and a stuffing box. And you can see that the cost varies with respect to the material of construction, you can have 316 stainless steel kettles in case the corrosion is high. You can have a gas lined kettle where the corrosion is medium. You can have homogeneous lead lined steel kettles. You can have cast iron jacket where the corrosion is minimum. Okay. And then you also, what is shown here is the installed cost and purchase cost. Installed cost is somewhat higher because of the other things that are that come into picture, like creation of support, creation of electricity connections, insulation, painting, so on and so forth. Okay. These things we shall see we shall see in greater detail in the module of project economics. Okay. Then you also have the cost of the jacketed or stirred vessel. Here, depending on the type of agitation that is used, okay, the kilowatt or the power of agitation, the speed and the material of construction, the cost varies, and the capacity of the capacity of the reactor. Then you have the for high pressure reactions, the purchase cost of autoclaves. You have a glass lined vessel, carbon steel and stainless steel. Okay. So you have cost correlations available. So do calculations, estimate the volume of the reactor. Then depending on what kind of reaction you have to select the material of construction. That is another issue that again will be covered in the courses of safety and risk assessment. Okay. We are going to have a brief introduction of it. There are several grades of stainless steel, 304, 306, depending on the temperature and pressure. Corrosion tables are available, okay, which give the extent of corrosion that occurs in a reactor over a period of time, and then you have to choose a proper material of construction for the reactor operation. Now again there is a trade off. If you choose a low cost material, then the price is low, but the durability of the reactor is also small. So you have to go for a trade off. With this theory, we will solve a small example on reactor sizing and cost estimation. I have chosen example on fermentation. I will first give the problem statement. Glucose is fermented to produce ethanol. The microorganism used is Saccharomyces cerevisiae. The temperature of operation is 303 Kelvin, it's close to ambient condition, and the rate expression with respect to glucose, the main reactant, is K into 1 minus C ethanol divided by C star ethanol. Now ethanol fermentation is inhibitory, which means the ethanol that is produced ruptures or it basically damages the membrane wall of the cells and it kills the cells. Therefore, as the ethanol concentration in the fermentation broth increases, the cells die, and there is an inhibitory concentration at which all the cells die. That is what is C star ETOH. That is inhibitory concentration. The inhibition factor is given by this particular bracket, 1 minus C ETOH, which is the instantaneous concentration of ethanol divided by the inhibitory concentration raised to exponent 0.6. Then Cg, glucose concentration, Cs, the concentration of the microorganism Saccharomyces cerevisiae, and the monod constant Cm. So essentially we have a monod kinetics with an inhibitory factor. K is the rate constant. So we shall list all the values. K is given as 1.6 into 10 to power minus 3 second inverse. C star ethanol is given as 90 kg per meter cube. Cm is given as 2 kg per meter cube. Okay. Michaelis-Menten constant Cm. Okay. Ethanol yield is 0.47 kg ethanol per kg glucose consumed. Then cell yield is 0.06 kg Saccharomyces cerevisiae, that we abbreviate by SC, per kg glucose. So, this is the information given to us. Now, we have to first estimate the time required for 95% conversion of glucose in a batch reactor. Initial glucose concentration in the reactor is given to us as 15 kg per meter cube. Initial cell concentration as 0.015 kg per meter cube. And the total volume of reactor is 10 meter cube. However, it is filled to only 75% of volume, or let us write just 75% capacity. That is better. Okay. So, we have to estimate the time for this particular condition. The second is that we have to determine the required flow rate for a PFR to produce same conversion as for the batch with same reactor volume. So, the reactor volume is same. I would write here in bracket effective. Why, I will tell you later. Okay. Now, here, however, the only difference is that the CS, the initial concentration of Saccharomyces cerevisiae, is not 0.015 but bit higher, 0.09 kg per meter cube. And the third thing we have to answer is what is the volume and cost for CSTR, continuous stir tank reactor. Here we write single CSTR, we are going to use only one for a single CSTR. Here the initial concentration, again initial concentration of microorganism is high. It is raised further almost 10 times to 0.95 kg per meter cube. And a flow rate of 3 meter cube per hour of glucose is maintained. The initial concentration of glucose is same as before, and conversion desired is also same. So, this problem tries to analyze a biological process of fermentation of glucose to ethanol in 3 types of reactors, and in each case we have to estimate either the volume of the process or the flow rate or the time. We shall see a detailed solution of this in the next lecture, and we shall also try to find out or we shall also treat a similar problem in case of an inorganic process, that is production of methanol from synthesis gas, hydrogen plus carbon monoxide.